The students. So today's class will continue what we completed the last class from that point forward. So we started simple band break. So in breaks you have two types. There is shoe and the band break. I think we left off at shoe break, and also maybe we derived this equation which you see on your screens. So this was derivation to know how much force you need to apply in both the cases of a clockwise or anti-clockwise type of motion. So this derivation was done in the previous class. Right, so we also defined terms such as self-energizing, self-locking, and grabbing. So these three phenomena are common for all the types of break, and uh, the self-energizing one being the most desirable one. Okay, so these conditions will be usually given in the question, or it will be asked for you to find once you start off with the numerical, right? So we did that for clockwise and anti-clockwise condition, and also for the long shoe. So before we start off with the simple band break, we'll solve one problem on this shoe break. So you have only two types of break, that is shoe and band break. So in band break again we have two more categories. That is, you know, this band break simple, and one more with the block band and block. So these two also we'll try to derive and also solve some numericals. So for now, since we have completed with the shoe break derivation, we'll solve one numerical on this. Right? We also saw the steps for solving the numerical. This is in case of a shoe break. Okay, for band break, I'll give a different version. For now, just follow this. So let's start off with the first numerical. It's the first numerical problem on shoe break. This will be typically given in the question itself. A single block break. Block break and shoe break both mean one and the same, right? So it is used machine which receive to 23.5 kilowatts of power at 1000 RPM, and you have the diameter of brake drum also given at 720 and material is same, friction brake shoe material. So both are same as with stars. It is a continuation of the problem. What do you need to determine? So sometime it will be given. So determine the effort of operating force, that is F. So this diagram also is possibly given in the question. So you have the drum, and this here is the shoe, and this here is the link, which is pivoted at one end and where you apply the force at the other end, right? So you have rotation in anti-clockwise direction or required for both clockwise and anti-clockwise, which means we need to design for both clockwise and anti-clockwise rotations, and you need to state whether this brake may get self-locked or not. See this condition, self-locked or self-energizing. So these conditions typically given in the question, or it will be asked to you for you to find out, and determine some important dimensions of friction. Important dimensions in the sense maybe the width of the shoe or height. Okay, on this dimension we already know it is a brake drum. Only we don't know dimension of this shoe here. So everything else I think we are good. Let's start off with this. Also in this question, it is to note that it has not mentioned any long shoe or anything of sorts. So therefore, as we saw in the previous slide for or the derivation. In the derivation, we actually think noted that this long shoe condition. The long shoe condition is not taken because long shoe is not given. So we'll just omit this data. Let's start off with a new. Okay, let's check it out. This is the first numeric key. Change the color. Data. The given was power. I think power is 3.5 kilowatt. Then I'll go back to the question here. Procedure, right, at 1000 rpm. So n is 1000 and diameter is 720 mm. Let's note that down. So n is our rpm, which is 1000 rpm, and given also is diameter d is of the brake drum. We come to 720 mm. Okay, what else is given? Just looking at the diagram, I think we can know some more data. So this is this distance. If you refer to our derivation before, right? So this is the figure which is taken out of the data handbook. So these dimensions also you need to note down. So from the force to the pivot point is A, and from the centroid of this drum to the pivot point is B. I think these dimensions are given. We can note that also. So this is A. A is 900, and you can see B is 360, and also this dimension is given. That is offset from pivot point to the circumference of the shoe. Circumference of the shoe here is C. So A, B, and C. So these three dimensions which are given from the figure in note down. This is a pretty straightforward problem. Okay. Let's note this down. So apart from this is for the lever dimensions. So this is let's take A is 900 mm. Looking at the figure, it is there in the data handbook. And B is 360 mm, and C is 40 mm. So this is the data given. That is the these are dimensions with respect to where the pivot point lies with respect to force. B is with respect to the center of the axis of the drum, and C is with respect to shoe, the contact point of the shoe with the circumference of the drum and the pivot point. Okay, so all dimensions with respect to the pivot point. So let's go back to the PPT. So let's go start off with step 1. So step 1 is you need to extract the material properties of friction shoe. That is, you find mu, that is coefficient of friction, and P. P is the pressure that is being applied, that is allowable pressure for that particular material and for the given material. This is, you take it from table 1311. Let's start off. So this is the solution part. So step 1, as we saw, extract the material properties. That is material properties of friction, or say block or shoe, both. So given was the material asbestos with metal, right? Go back to the question. Let's set out the question once quickly. So this is asbestos. The material of the drum is some material. It is not same. It is some minus. The friction brake shoe is given as asbestos. Both can't be asbestos, right? Both can't be flexible. So one of them has to be asbestos. Let's say asbestos with some metal is not given. So for this combination of asbestos and metal, no, we just need to check table 3.13.11, and let's say from table 1311. So let's out the table. Yeah, right. So this is table 11. I can see here asbestos block on metal. Okay, asbestos block on metal, asbestos on metal short action, metal on cast iron short action. So short action may mean that it is the break is very small, and also it is lubricated. Okay, so when it is lubricated, you don't need that much of braking action taking place. So therefore, for short action, I guess only the shoe will be small. So in this case, in the dry and greasy condition, we can assume here. So both these conditions were again not given in the question, whether it was dry or greasy. So what we'll do, we'll take this combination here. We'll assume asbestos block on metal, and it is undergoing a dry friction. Okay, so that comes around 0.44 to 0.4 is given in the reverse order. So this is coefficient of friction. That means mu is between 0.48 to 0.4. So we'll assume just midway between this. So let's say mu is 0.44 something, right? Somewhere midway between this. Then is assuming dry condition. Okay, you can assume greasy. Since it's not given, you can assume greasy, and you can also solve this. No problem. Again, is the design, so final answer doesn't matter. You need to concentrate more on the procedure what you are following. And let's say next thing is pressure. Let's go back to pressure. Yeah, allowable pressure. Since we have assumed this condition here, so it is 0.28 to 0.11. Okay, so halfway between this, I also can take, let's say this is allowable pressure. Allowable pressure, that is P equal to, it's in between 0.28 to 1.10 megapascal. As taken from the table. So let's take halfway between this. Let's choose any value between these two. So getting 0.69. Let's take this pressure. This is a small letter. Don't confuse with power. So small p is 0.69, right? Newton per mm squared. Okay, so this is the pressure. This is in which the brake shoe is acting. You can allowable maximum pressure which you can apply on this particular brake. Right. Right. So with this, step 1 is done. Right. So step 1 was extract mu and p. We have done that. Step 2 is you need to find what is the torque acting. This is a classical equation which we were using since a long time. So we'll take this equation here and plug it into the value. Let's say step 2 is find the torque, right? Yeah, torque. It's torque acting on brake drum. Brake drum or shoe, both are same. Brake drum or brake shoe, right? That we know the classical equation. Power P is equal to is 2 pi n P over 60,000 in kilowatts. So we have power. Power is 3.5. Right, 3.5. This is 3.5 equals to 2 pi n. RPM n was given as 1000. T or MT. You can write it as T or MT over 60,000. So this, I think, you'll get the torque. Torque, which is here in Newton meters. So if you're calculating, you can just check it out once. How much your torque comes to. Right. So once we find the torque, let's move on. In the meantime, move on to the next step. Is anybody calculating? Just post it in the group chat. Right. Let's see what's next step. The next step is to find normal and tangential force. So the reason why we are finding these is it is required for finding the braking effort. Right. So how much force is actually needed to be applied at the end of this. The end of the lever. Okay, so that is required to be found. Let's do that. So step 3 is normal and tangential friction force. So step 3 is find the normal and tangential force. Force or friction force, both are fine. So normal force Fn was given as 2 times torque over mu and d. This is there in equation on 3.16 F. So we know all the data on the right hand side. Just substitute and extract the value. So this is 2 into torque. Torque, anybody found? Let me just calculate. Right. So this is around 2 to 4.4 Newton meter. So that means this will allow as 2 to 4.4 into 10 power 3 Newton mm. Right. So this is the torque. Right. So now we have found the torque. You can just substitute here along with the other values. So this is 2 to 4.4 into 10 power 3 over mu. We just found it in the previous step 1. Mu is 0.44. So let's write that down. 0.44 into d. D is the diameter given in the question, 720 mm. So this is 720 mm. So with this, we can find what is the Fn, that is the normal force, right? Right. So the next one was to find the Ft. It is the tangential force. Only just mu times n, Fn. The tangential force Ft is equal to mu times Fn. So this is also given in equation. I think it's just below this equation. Just below that. It's evident from the figure. I think is given. Just calculate that value there. There is 2 into 2 to 4.4 3 4.44 times 720. Okay, so we have got friction force Fn, the normal force as 1416.67 in newtons. I think I'm right. 24224 0.43 0.44 times 120. Yeah, right. Okay, so once you got this, again this is got 0.44 times the same value 1416.67. So this is the tangential force 0.44. So this we are getting around 623.33 newtons, right? So this will be required for finding the actual force which is required for braking. Right. So step 3 is done. Move on to step 4. Step 4 is braking effort. Braking effort for operating. Right. Let's start this. So this is step 4. That is braking effort. Braking effort or force, you can say, or force. So in the question he has asked for both conditions, that is clockwise and anti-clockwise. So we'll start off with for clockwise first. For clockwise, the force F is given as Fn times B minus mu C over A. This is given equation 13.16C. Force F was given, so we know Fn here, we know B, we know C, we know mu A, everything is known. In the RHS, everything is known, just only thing is to substitute. So Fn, let's go back to Fn 1416.67. It is 1416.67. Right. B, C, and A. So 360, 40, and 900. So B was 360 minus mu 0.44 times C, it was 40 mm. All those data we extracted from the figure given in the question over 900. Right. Let's calculate this and find the force F for clockwise. Similarly, let's write F equals this much. Let's try calculate and post it in the group chat. For counterclockwise, the equation goes like this. There is F equals to is Fn into B plus mu C over A. This is also given. There is 13.16 D. There's a sign is different. Nothing. No other change. So essentially, what I can do is copy everything here and paste. The only thing different here is the sign. Right. So anybody calculating, just let me know in the group chat. Is 1416.67 times 360 minus 0.44 into 40 over 900. So for clockwise, counterclockwise, I'm getting 538.96 newtons. Similarly, let me find out for the counterclockwise also. For counterclockwise, just the sign change. I'm getting the force F as 594.37 newtons. Right. So both clockwise and anti-clockwise, the force is found. Right. So step 4 is done. We need to find the force for both clockwise and counterclockwise direction, rotation. So the last step, one step before the last step, is checking for self-locking. Self-locking, we know the condition. The value of mu and c should be greater than or equal to b. Right. So this we on the derivation. So this is b and this is c. So b should be lesser than mu times this dimension c. Right. Next step, step 5 is check for self locking. So for self locking, the condition is b is let's note it down separately. So b is what you have in the data is 360 mm and mu times c. Mu is 0.44 and c was just 40 mm, right? So multiplying this 0.44 into 40, you're getting 17.6 mm. So you can just assess the situation here. So B is obviously greater than mu times C. Okay, so it is greater, so which means it is self-energizing. So this is a required condition. This is a desirable condition when designing a shoe brake. So since this B is greater, so we can write so therefore this brake is self-energizing, or you can say not self-locking. And the question I remember they had given check whether the brake is self-locking. So you can just say it is not self-locking brake. You can say that. Okay. Although sometimes it will be asked in the question that when this particular brake will be self-locking. So in that case, this mu being constant, you can keep this constant and you can just send it over to the other side and find out when at what particular dimension will this become self-locking. Okay, this value of c will become self-locking. In that case, b over mu will give you some number. So that number will be value of c. So you can say until then you can increase the value of c so that you don't have the self-locking phenomena appearing at all. Right. So step 5, check for self-locking. And the last step, step 6, that is to find the dimensions. So all these equations are I think they're one below the other. Let's note that also. So step 6 is dimensions. dimensions of block. So area, first thing is required area. This is ABS given in as Fn over P in equation 13.16 G. So normal force, I think we already found out how much that is. 1416.6. 1416.67, and this here is a small p. It is the pressure. This is over 0.69. So with this we can get the area. So 1416.67 over 0.6. So that is coming around 2053.15 mm square. So that's the area which is in contact, which is the required area of the brake shoe, so that it stops the vehicle or the drum in this case. Okay, so let's see what else is required. Width of brake lining. So all of this is given in this table here. So table 13.6a. So the dimensions. So from table 13.6a. So let's look at the table. Oh, it's not there here. Let me just open that. Right hand. 13.6a, right? Here 13.6a. Here wheel drum diameter was given. So what is given in our question is 720, but here I don't think we have 720. So we have this 630 and 800. 630, right? So 630 and 800 we have for, so we need to interpolate somewhere between these two values. So for let's say D equals to 630 mm, width was 200 mm. This is width of shoe I'm talking about. And for D 800, we have width equals how much was that? 250. It's 250 mm. Now we have D is our question here. That is what we have is diameter 720 mm. So for this, what is the width? So 630 and 800. So if you interpolate, I think you'll get somewhere between 225, 27, something like that. So we'll keep 225 mm. This is by interpolation. This will keep it as VD. So now we got BD. You can find the rest of the equations. Okay, so BD is extracted. Now that we know BD, we can find BL, that is the width of brake lining. So width of brake lining is BL is BD minus 5 to 10 mm. You can decide that as given in equation on 3.16i. Okay, so BD is 225 as got, and let me just assume 5 mm. They can go midway or anyway, it's just 230 mm. Right, so that is done. The dimension, brake length, then projected length of lining. So projected length of lining, right? This projected length of lining. Let's say this is given by L, given by A, BS. That is the area of contact over the brake lining width. Okay, so this is an equation 13.16J. What's our absolute area? 2053.15. 2053.15 over brake lining 230. So LL, which is the projected length, let's calculate this divided by 230. You're getting 8.93. Okay, this is the shortest length of the shoe. Okay, projected length of lining. So the shoe which is there like this, right? So let me just draw it for you. So projected length, you have the brake shoe which is mounted like this, right? So curved surface like this. You have this area. So this area, projected length of lining. So if you just flatten this curve here, it looks something like this, and this length is what he's talking about. So flattening of this curve here, there is the projected length, which is 8.93 mm. I think one last dimension remains, semi-block angle of contact surface. Last dimension here, say semi-block angle. Theta is 2 sine inverse of L by D, is given as equation on 3.16K. So in all dimensions here, so it is 2 sine inverse of 8.93 over D. D is the diameter of drum, 720. So this we can find how much we have of theta, the semi-block angle. Is 8.93 over 720 sine inverse of that and times 2. So I've got theta as 1.42 degrees. That's it for the dimensions part of the right. So we are done with the numerical, and this is the only numerical we are going to do. Is all of them follow the same procedure as such. Some of the other data will be given or maybe missing, and some problems they ask you to find whether it is self-locking or not. So this step is where some amount of distinction takes place. So this step 5 here for self-locking. So once you have checked whether some problems may specify that, find the dimension in which self-locking occurs. Okay, so in that case, just you need to find the C and give us separate note. So for example, in this problem, if you wanted to do just as an addition, B I would keep as it is 360, and this I would equate to mu C. So that is 0.44 times I would leave the C as it is. So in this case, if I were to find the dimension of C, is just 360 over 0.44. So this is coming. C is 8.18 mm. So this dimension here is what is required. Suppose it will become self-locking in this case. So at this dimension, you can say it is then if C is this much, then the brake will be or will become self-lock. Okay, this time the brake will become self-lock at this particular dimension. This dimension is here. This C, which you can see here, right? So B and C are here. So if this dimension crosses that 818 mm, so then it will become self-lock. So this kind of small twists may be given, but the entire procedure will follow the same thing. So we have the same thing. So even dimensions follow the same principle. So not much difference what we can see in this numerical here. So any doubts you have, just let me know in the group chat. The next class we'll start off with the band brake.